Hello and welcome to the eTech podcast with me, your host, Ryan Morn. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. For today's podcast, I am joined by someone who is a bit of a legend, to be honest. He has been a true pioneer in a very exciting field of the semiconductor industry and electronics, and has got an absolutely amazing story. So really pleased to welcome Geoff Haynes to the show from Inspirit Ventures, and he's involved with a number of different businesses and a massive expert in the field of GaN technology, and he's really kindly agreed to do this podcast, so build up on some of the content we've been producing, talk about GaN and applications of gallium nitride systems and how that's sort of coming into effect. So, Geoff, thank you very much for agreeing to do this today.
You're very welcome. I love talking about it.
So, start off by telling us about yourself, you know, your background, how you got into doing what you do now.
Oh, goodness. It goes back to when I was about 7, I guess, on a train journey with some bits and pieces from a drawer of my father's. There was a battery and a bulb and some fuse wire, actually. And all of a sudden, they all connected and the bulb lit up. So that was my light bulb moment. But moving on quite a long time, while I was while I was at Kingston College of Technology studying electrical engineering, because electronic engineering wasn't really a subject at that point in time.
Yeah.
We talk about valves. I don't think we really got into transistors. But it was a sandwich course, and I met a guy who was working with the Hoover Company, and they didn't have electronics, so they seconded him to Marconi to get his experience in terms of electronics. And the two of us were given a task to solve a problem on a production line with an overtone oscillator that didn't always go off on its proper overtone. It was interesting because it had no inductors. It didn't have a classical tuned circuit. Nobody really understood why it worked.
Yeah.
So we got in and we went up to Lisle Street and bought some variable capacitors and played about with this thing. Finally discovered how it worked and rewrote the patent they had on it. And that was an amazing experience. The gentleman, John Roberts, that I was working with, if we fast forward another, 40 years, the two of us, along with Gervin Patterson, started a little company called GaN Systems, because previously John and I had done a lot of things together in different companies around the world, not always at the same place at the same time, but always in communication.
Yeah. And
the last thing that we had done was to spin out strained silicon from the NRC in Canada to form eventually a company called Semiconductor that went on to get sold. And John and Gervin had been passing their time building super audio systems with line speakers that were phase controlled. And they decided that what they needed was a Class D amplifier.
Yeah.
Somebody said, if you're going to get into Class D, what you need is a really fast switch. And there's this stuff called GaN. And down the road at the NRC, they're building GaN on silicon carbide for RF communications in space. So John went toddling down there and said, look, can we get some of these transistors? And they said, yeah. By the way, you spun out a strained silicon, didn't you? Could you do the same thing for the GaN? We looked at RF and decided that was an interesting market, but it wasn't as large as the potential for these fast switches in power systems. And the concept of GaN systems was born. And another 15 years on, We last year, and last year or the year before, sold the company to Infineon.
That's
I
small
think
business.
yeah, absolutely. So I think that verifies the fact that we didn't waste those 15 years. Actually, in the middle of that, I did exit because we produce perfectly good transistors, which are pretty much the same transistors that are being used today. But we loaded them into distribution, not really certain that they were really going to work well. But there was a thing called the Little Box Challenge, the Google Little Box Challenge, a prize of $1 million for anybody that could build the smallest, most efficient converter for a solar installation.
Right.
And eventually, I think 13 of the 20 finalists used GaN transistors, and most of them used ours. And so if you think about, I don't know, that must be nearly 10 years ago, those transistors really haven't changed very much. But until a year ago, the main market they were serving was just making much more effective small power blocks for game computers.
Yeah.
Works extremely well for low power applications where you want something small and very, very light.
And that's even in the last year or two, probably 2 years ago, an awful lot of people wouldn't really have been aware of GaN technology. But in the last couple of years, basically the power brick that charges your computer or whatever has got very small and doesn't get hot anymore. So you can't put your feet on it to warm your feet up in the winter. And that's because they've gone for GaN technology inside those power converters that are used to convert mains power for DC for laptops and yeah, like say game consoles and computers and things like that. But it's actually the applications of GaN, and you've touched on a few already, but it's an incredibly deep and broad technology in terms of where it brings value, isn't it?
Yes, it is. But the challenge becomes, it's really sad because we were entering the market a little after silicon carbide, but silicon carbide has taken the front seat in terms of revolutionizing higher power converters. And it did so because it didn't need to switch fast. It could switch high voltages, and it was a much smaller die and would operate at high temperatures. And our friends at Tesla decided it was the right thing to do in a car, so everybody followed suit.
Yeah.
And to drive a technology, you need extreme volumes.
Yeah.
Right now, the volumes are beginning to grow on the laptop converters, but it's nothing like the focus that's been put on silicon carbide. It's interesting because, as I say, I left the company after that Google Little Box Challenge because I could see, and the company supported me in that there was a real need to engage not with customers, but with the academic community, because what we had to do was solve all the problems of how do you package these things without just getting in the way. The capacitance and the inductance of a package becomes really significant at the frequencies you want to switch at. And then if you've got a different transistor, you probably want to put it into different types of circuit where it has more advantage. And having done that, you then want to go on and think about how you'd build a system. And so Alex from EPC, Analog Devices and GaN Systems provided me with some money to buy prizes for the 12 universities in the UK that were in the virtual power center. And they crowned me as industry champion. And we just went around piling together the bits of technology we needed to push this thing forward. First thing we did was to spin out TTPi from Nottingham, who threw in the idea of being able to contain the EMI that you create when you switch fast. And they came up with ways of working together, in fact, with RAM Innovations, one of the other companies that I invest in. They created an embedded packaging technology that allowed us to be able to put these big die in, or I should say high power die. They're not, they're very small actually. High power die into a small package, get the heat out effectively and reduce the inductance in the switching loop so that we could actually get real performance out of a building block. So that's what started the activity that I'm involved in now, which is Inspirit Ventures. Again, running around looking for all of those end users that can benefit and trying to bring them together in a collaborative activity. We've done quite a lot of work with various Innovate projects. We just in the process of finishing a project that brought together RAM Innovations, TTPi, PPM, British Aerospace as an end user, Computronics from Cambridge to do all the modeling for us, and Cambridge GaN Devices, of course, our own UK GaN transistor company.
Yeah.
And we've been exploring what you can do with putting their transistors into a little pack. And now we're looking to move on to involve some of the users in a jointly funded activity to build some real systems that would fit into any power application, from space right the way through to electric aircraft even.
Yeah. And what is it, maybe because sort of peeling back to first principles on what is it about GaN technology that's so exciting for power conversion?
Well, it's the fact that you can switch much faster. If you think about a switching converter, you're only taking power while you're switching. So if you could take this to the extreme, as with my latest involvement with QPT, they're trying to switch GaN transistors, existing perfectly good transistors, switch them at 1 nanosecond. Now, if you think about the switching edge at 1 nanosecond, let's go quite fast and switch at, let's say, at a microsecond, 1 megahertz. We've only got 1,000th of that period that we're actually taking any power.
Yeah.
Now that makes a real difference. And having switched that fast, nobody's going to want to drive a motor at a megahertz. They're looking for a few, maybe 8 kilohertz, 16 kilohertz at the most. But if I'm switching that fast, I can build a sine wave at whatever frequency they want. And just think about with your background, you'll know exactly what you can do. If I give you a sine wave to drive your motor, it makes all the difference.
Yeah. You can really clean up that motor.
So there's your ultimate answer. It is the thing that switching at speed does for you is it really reduces the weight and the size of a converter. And if you think about that in terms of operating cost in an automotive, for instance, as BMW say, every watt counts.
Yeah.
And it's not just the power, it's the power you expend in moving the vehicle along.
Yeah.
So there's CO2 and energy to be saved.
Well, the efficiency point is a really strong. Power converters are absolutely everywhere, aren't they? From just on my desk at the moment, I've got all sorts of different devices with all kinds of different power conversion in. There's the big obvious things like traction motors in electric vehicles, but there's power conversion literally everywhere. Solar panels, battery systems, monitor in front of me, the LED lights that's creating a nice background for me, et cetera, et cetera. So it's saving the most efficient power is the one you don't use, isn't it? So
Exactly.
Taking those losses out, and I think that we're all familiar with things have got a lot more efficient than they were, in power systems and such like. But there's so much more electronics devices, you talk about things like AI data centers consuming more power than small cities, and that kind of, a lot of that power is lost in power converters inside the data center to reduce voltages and convert from AC to DC and such like. So we're in an era where energy is absolutely everything, and like say, every watt counts. So very really interesting.
It's not difficult to see why I'm so excited. And it's lovely. I get to play with other people's companies without any of the responsibility. They either enjoy what I do or they walk away.
Well, and of course, I mean, I'm sure you won't mind me saying, but I mean, you started a career in electronics before electronics even existed, and one could infer from that.
No, be careful. But before useful transistors.
Okay, before useful transistors.
We were using green spot and red spot germanium transistors when I was at college.
Yeah. So, you could say that some people who weren't quite as enthusiastic about what they do would have been playing golf for a long time by now. Or some other pastime that doesn't involve working, but you're still very much up and at it, involved in lots of different businesses and really pushing technology forward even now, aren't you?
Yes, and it keeps you young. I mean, the fascination really came with working with the universities so closely and starting to spin things out. What's fascinating is to watch the effectiveness of putting a really good student who doesn't know it can't be done together with somebody like John Roberts, my CTO at GaN Systems, who knows everything but doesn't have the time to focus on any one thing. When you put the two of them together, magic things happen. So you can walk into with one of the things that I think we really missed from not continuing the Power Electronics Center was the fascinating things that would happen when you had £50,000 and you pulled a number of professors that had not formally worked together, put them in a room and give them a task and give them 6 months to do something with it. It's just fascinating what you can do. We had so many little projects where we brought the various pieces of the various universities together and created things that some of them have actually spun out as a result of it.
Yeah. Oh, brilliant. Yeah, fascinating. And so in particular, you mentioned already there's sort of the competition, if you like, between pure silicon carbide devices, which have got into the market, are pretty well known now in things like traction inverters and power conversion, higher voltage power conversion systems. We've not seen GaN devices used particularly at scale today in applications like that. The first question is why do you think that is so far? And, do you think that's going to change?
Yeah, I have some very strong views on that, actually. The first is that, of course, as I said, silicon carbide was useful anyway in those systems as an advancement because it would switch the higher voltages and was very effective in doing that. Initially, ordinary packages were used and things could be done very quickly. As soon as you start to look at trying to get any advantage out of GaN, you're wasting your time unless you switch faster than you would switch a silicon carbide device. They really don't compete. Now
that's interesting because most people understand that silicon carbide devices are already a lot faster switching than conventional IGBT.
Well, yes, but it's interesting that having started an activity between TTPi and RAM Innovations, building embedded packaging, that was done in order to enable GaN. But what's happening is companies now are asking to put silicon carbide in there because suddenly they do recognize silicon carbide will go faster, but they can't do it in the standard packages. You've got to build a little module, and you've got to worry about the inductance in the switching loop. So silicon carbide is beginning to really take advantage of that technology that I was interested in developing for GaN. But as you start to say, wait a minute, I can go faster than that, and you start looking at applications where the 1200 volts is not needed, 800 volts is not needed, 400 is, and you're not looking to drive a motor, but what you're looking to do is make some sort of DC to DC, 800 volts to 48 volts within the car, for instance, and bidirectional as well. A DC to DC converter is where you'll see GaN really starting to eat into all of the OEM EV platforms now. When you start looking at driving motors, at first sight, you just don't need the high speed. The last thing you want to do is to switch the windings at any particular speed, because they'll break down, as you well know. But if I can switch fast enough, as QPT does, to give you a sine wave to drive your motor, then the world changes. But that's the next step that's coming. So GaN is finding its way into things. The real focus for the GaN industry right now, I would say, with the low voltage parts, our friends at the EPC are doing extremely good stuff at low voltages, especially in the LiDAR applications for all the autonomous vehicles. If you look at the Infineons of this world and Cambridge GaN devices, I would say their focus right now is on the big data centers. The power supplies for those, where actually reducing the size becomes... I was down at the CSAC yesterday, and it's surrounded by enormous buildings that are full of systems for storage and the internet. Absolutely. And if I could halve the size of the boards in there, I wouldn't need to build a new building. I could just double what's inside the existing one. So there are enormous markets out there. I say they don't compete. I shared a platform with Guy Moxey from Wolfspeed, and we totally agreed that silicon carbide, actually, there's a little bit of a problem now. It's got to the point where everybody's got so excited about it that we've poured so much money into it, with the Chinese doing their usual thing. All of a sudden, silicon carbide wafers are ridiculously cheap, because the EV market isn't taking off at the rate that everybody thought it would, and everybody was throwing money at it. So that's the other thing that I find a bit frustrating. Everybody focuses on the cost.
Yeah.
Actually, the cost isn't important. The cost will be what it has to be. And usually it is cheaper. If you look at that silicon carbide situation, with wafers changing hands allegedly at $400 a piece, that is very cheap. Whether that's sustainable, I have no idea at all. But all of a sudden, we at GaN Systems were told that we really had to use a silicon substrate because it had to be very cheap. Now, the GaN process has half the number of process steps. Diffusing into silicon carbide is extremely difficult to do. Silicon carbide wafers require an awful lot of energy to make them. Whereas if I put as soon as I put the GaN onto a silicon wafer, I put a chain round it, because now the substrate is conducting, and so my channel, which is an electron gas, is going to break down to my substrate. And I can only generate easily a breakdown voltage of around 650 volts. That's good enough for 400-volt systems. But if I'd stuck with what we did originally, our first transistors were 3 kilovolts, and we got 25 amps out of it. I remember standing up at an iPower conference. Or was it no, it probably wasn't. Anyway, a conference where somebody presented a story that you couldn't build a GaN transistor that was going to handle more than 10 amps. I held a 25 amp 3 kilovolt transistor up immediately after him. So I see GaN is about to, with vertical structures, with better substrates, even on the silicon, with the possibility of putting them onto sapphire or silicon carbide. We're going to see high voltage GaN as well, starting to find its own way into new applications. But if we look at higher powers at higher voltages, that's where the wall speeds are going. They're focused on 6 kilovolts now, and I'm sure they'll be pushing up towards 10 kilovolts. And that takes us into the grid, for goodness sake. Yeah. Wow, what a playground that'll be.
Yeah, well, it's a big area, isn't it, in grid connected systems, and because the big sort of transformers and such like that you use on grid are pretty inefficient, and they could be significantly improved with active electronics. So wind power is another big area where going to sort of active electronics.
Exactly.
The original wind turbines had very complicated gearboxes to try and get the generator frequencies right. Now they don't bother about any of that stuff. They just correct it all with electronics afterwards. So it's like some big transitions in the energy system coming through on this. I'm going to loop back again because you touched on a really like a enormous part of it. So we think about GaN. I think a lot of people think sort of conventional transistors, silicon carbide transistors. It's quite easy to get your head around the production technology, the sort of topology of those parts. One of the fascinating things for me anyway about GaN is that there's so many different possibilities in terms of substrates, topologies, construction technology even. It doesn't even feel like we've even started yet to exploit the potential.
That's absolutely true. There are so many different ways we can push that forward now. The silicon carbide has focused very much on building conventional structures with new materials. As soon as you move to GaN, you have the prospect of having an electron gas. And my friends at Sheffield would combine that with a whole gas as well to balance out the charges. But then somebody comes along and say, well, we could build a vertical structure, and perhaps we could do that with GaN on GaN itself, which would solve some of the issues of the early GaN transistors. The really big problem was that the crystal mismatch between the silicon and the gallium, the AlGaN epitaxy on it, would put a physical strain on the wafer. So unless you made the wafer very thick, making it very difficult to get the heat out of it, then the whole thing would bend. And that was a real issue that we've been struggling with for some time. But if you start to look at using alternative substrates, then you get away from the fact that you have the breakdown to substrate, and you have lots of other advantages that start to come in. You can make the substrate much thinner, get the heat out more effectively. So there's an enormous field of academic research, and then new devices that we'll start to see coming into the market. I think the first one that underlines where I think we should have been at the beginning is the devices that power integrations are producing, 1750 volt GaN on silicon carbide devices, I think. And that's giving them the opportunity to start fencing with the bottom end of the silicon carbide activities. It's horses for courses. It's not competition at all. There are so many different applications and so many different ways of achieving them. It's a fabulous world it's getting to the young people that can really actually make this happen. That's become part of my mission.
Yeah.
Because we got to have those young students to work with us old fogies.
Yeah, and it's an interesting thing in that, I'm a little bit younger than you, 1 or 2 years. But even when I started out, I think sort of a lot of fields that are super interesting now weren't really things that people even thought about as being interesting. The sort of on the engineering degree that I did, all of the stuff to do with like motor technology and generators and grid stuff was all the same as it had been for forever, and it wasn't an area that was particularly innovative. And you certainly didn't have young people thinking about being electronics engineers or embedded software engineers and such like, because those things they weren't in the consciousness. But now we do have these amazing opportunities for people, even with talking to my own family about what they're going to do when they go to university and stuff. It's amazing what you can do now, and the opportunity that there is. Really, how we push that forward is going to be interesting. So I have a technical question for you, or maybe it's a technical question, I don't know. But one thing that I have heard repeatedly on GaN devices is that one of the issues for applications where you have like a really long life cycle requirement, so like durable goods, traction inverters for cars as an example, or DC-DCs in cars, or grid connected equipment, where you want to put something on the grid and you want to walk away and not come back for 50,000 or 100,000 hours, so it's a long life cycle. And I've been told by different people in different ways that effectively normal transistors and silicon carbide transistors, people understand the degradation mechanisms, and the life cycle sort of analysis is easy to do. But with GaN devices, there's a sort of challenge in these more durable applications in predicting the degradation mechanisms over life. Like it's just not understood enough about what's going to happen to these things and what kind of reliability factors you have to build into the system. Is that something that you're aware of, or do you think that's as one of these? It's a problem that's being raised by someone who's passionate about silicon carbide and wants to come up with an excuse for why they didn't do it with GaN?
I'll give you a very biased answer to that. I'll admit to the bias. The problem with any new technology, and so our GaN transistors use an electron gas for the channel, and that's different from the sort of things that we did with transistors with junctions for years. And so there has been a lot of experience. Because it's really different, two things happen. The applications that GaN really gives advantage to are the ones that you described, the ones where we bury it under the road and it's got to stay there forever. Or we put it in a traffic light where the company that made the traffic light becomes responsible for the performance of that over its life. And if anything goes down, and it goes down for too long, they have to pay money. Those are really, really sensitive markets. So there is a real focus on any new technology in terms of understanding what the lifetime mechanisms are. And unfortunately, the other thing that happens is that the users don't want to change. When QPT has won a prize with ABB to build a new inverter system for motors, and in going through the final engagements for that, the people within ABB split into two groups. And caricature here, those people dealing with the motors could see a real advantage in being able to switch fast enough to be able to create a sine wave at the frequencies they need to drive the motor.
Yeah.
Great thing, let's go ahead. The people that had to deal with the drives were very cautious because it is new. They're going to be responsible for making this thing happen, and they do have to worry about all of the reliability. But equally, it was going to have to mean a lot of new learning.
Yeah.
And so there is a tendency for companies, quite rightly, to worry about the long-term reliability, but to over-egg those problems because it's good to push it out there because they don't have to make the change.
Yeah.
Now, if you look at the academic side of things, focusing on new ways of using it is not interesting to those end users for that reason. What is worth investigating is all the things that could go wrong.
Yeah.
So you get an enormous focus on the things that might go wrong. And I would say that, to put it simply, GaN transistors are automotive qualified. And they're running in space. GaN has been, when we first started the company, there were GaN transistors flying around the world in space in communication systems. Yes, there are different problems. They have to be understood, and there has to be some proof. And it's nice to be able to say, that guy over there has already done it, so I'm safe. So I think they're over-egged, to be honest. What is really interesting is nobody worries about the fact that when you increase the temperature of any electronic system, if I understand correctly, its reliability goes down by a law which is related to an exponential of the temperature itself.
Yeah.
Arrhenius, I think. So all these people that really worry about the reliability of these systems, but then say, I want to run it in a car and I want to run it at 300 degrees C, it's ridiculous. The thing you have to do with a GaN transistor is keep it cool. And if I'm going to switch it to 1 nanosecond every microsecond, it ain't going to be on for very long at all. So I'm keeping it extremely cool, and I suspect I'm gaining enormously on life if I really do that. And if I put it into a package and I embed it, I don't have any bond wires, and the things that go wrong first are the bond wires come off. Now I've got a thick copper plate that's making all of those interconnections, and we proved very quickly that that's a lot more reliable. So I think those things, they are real concerns. They have to be addressed, but I don't think they're the problem they're made out to be.
And would you think it's a fair comment that actually, in general, the reliability of GaN devices in practice is actually incredibly good, because you're getting rid of heat, you're improving efficiency, you've got these different junctions that don't tend to break down in the same way that conventional transistors do.
We don't even have junctions. So they're red hard as well. So if you want to fly them, you haven't got the problem of cosmic particles just folding up your whole electronics.
That's the sort of radiation. They're inherently radiation proof, aren't they?
Absolutely correct. And that makes them simple to build, by the way, because you don't have to make any diffusions. You're going to grow an algan epitax, and then you're going to create an electron gas on the top of it. And you're going to connect to the two ends with ohmic contacts. And that's about all there is. It's 5 or 6 processes or mask steps instead of perhaps 17.
And I mean, so that probably quite nicely segues into another question that I had. Looking at like time immemorial, the problem with the semiconductor industry, power or not, logic or power, is that, the plants that you need to build semiconductors cost zillions to build. And I think actually a podcast guest earlier a few months ago made a comment about owning a fab is a good way to lose a lot of money, or spend a lot of money, certainly. So technologies like silicon carbide are super capital intensive when you look at the investments that have gone in building the supply chain up for silicon carbide devices. Is GaN potentially going to be very disruptive in the future, because actually you can build facilities to build the stuff much more cheaply than you can for conventional power devices? Do you think that's an element of it?
Well, again, from your own personal experience with a little bit of time at Inex, you'll find that one of the reasons we were really interested in going for GaN devices was that you're not talking about super tight dimensions. Half a micron is already as far as you really want to go. You've got large amounts of voltage in there. So there aren't the extremely expensive investments in terms of the photolithographic activity, and a half micron CMOS fab that's going to go extinct unless you do something else with it. It's a great place to build GaN.
Yeah, now there's a familiar story.
Putting the epitax on the wafers in the first place is a complex activity, but there are plenty of people around the world. And look at the UK. We have IQE headquartered here in the UK, and they make a very large number of wafers, and they're quite capable of producing very good GaN wafers, or GaN on something wafers. Here in the UK, I can think of at least 3 fabs that you could build GaN very effectively in. And if you say that this market is going to be much more, if you can only use these things at the module level effectively, because you want to put all of the fast switching pieces in a special package, then no longer do you have a situation where you're building hundreds of millions of one thing. You're building perhaps 100K of 10,000 things. And so you've changed the way that the packaging market goes. I listened to a lecture by the CEO of one of the big OSATs who said that is their biggest challenge now, that they are faced with having to do things. Well, think about PCB shops. We still, if you've got a lot, you send it to China. But if you want something done quickly and perfectly good quality and volume at a reasonable cost, you can get done in 20 places in the UK. So I see lots of little fabs, frankly.
Yeah, and so there's a really interesting point that effectively you're moving the power device down the value chain towards the end application. So rather than working from a catalog of mega high volume manufactured standard parts, you're much more into application specific system, not system on a chip, but very highly integrated hybrid system that's closer to that end point. So that kind of, that tips the whole electronics industry on its head in terms of how we're used to doing things.
In the early days of looking at little modules with GaN in, on 2 occasions that was really demonstrated to be effective. One was in a conversation with Huawei, who were looking at using GaN for power supplies in large communications systems. And the attraction for them was that if they could build a DC to DC converter in a package, if the technology changes, that module can still look exactly the same, but it can have completely different technology inside it as it develops. So now you've got your communication system and you want to update it. You haven't got to tear it apart. You can actually update each of the modules as the technology improves. Exactly the same comment has been made in the automotive industry. They're really beginning to look for a piece of the system that can be treated as... They're faced with an amazing problem, aren't they? Perhaps it takes 5 years to develop a vehicle that has to be around, well, historically would be around for perhaps a 10-year life to make it economic. Battery technologies that can change in a 6-month timescale. So you really have to modularize things so that you can adopt new technology without tearing the whole page up.
Yeah, it's a very good way of putting it. So then, for you now, you've been through a couple of journeys of businesses that have gone from ideas to then very successful, scaled up businesses. You're working now with 3 or 4 really interesting sort of startup companies in effect. And you touched on RAM Innovations, and they're a really interesting bunch doing their packaging work, TTPi. You very briefly mentioned QPT. So tell me a bit more about QPT and what they're doing and what their plans are.
Yes. So that comes down to, I had missed that one completely. They'd been around for about 4 years, I think, working very much in stealth, just as we sold GaN Systems to Infineon, and I was starting to look around for the things that I might be able to invest a little bit of money as well as my time into. And QPT emerged as really the next step in the whole game. What they were looking to do was take the transistors that we'd made and are now production devices and look again at the way they're used in a system. And Rob Gwynn, the CTO, said, look, why on earth would I not switch these things as fast as they can go? So his objective is to take the switching edge and get through it in a nanosecond. Now we've taken all the power we're going to, and we can sit down and wait until we need to have the next pulse.
Yeah.
Or edge, not pulse. The pulse remains. So that to do that, you've got to think right from the beginning. The first thing you need to do is say, if I'm going to switch the output in a nanosecond, how fast is my gate going to have to go? So I need to look at low voltage transistors that can go very fast. And so EPC makes some very good devices. We could use those for our driver. We need to be able to isolate that driver. And what they started with was a little microwave transformer. So very cheap, very simple little thing that's going to allow me to be able to transmit very fast signals across an isolated barrier. And that was their first patent activity. But now I've got my output switching very fast. The next thing I've got to do is to match it to my load, because otherwise, if you put any sort of transmission line on it, connecting it to a motor or anything else, it's just going to ring like mad.
Yeah.
So what I then need is, once again, some passive components that are going to be really effective at microwave frequencies, because my edge has now harmonics up in the perhaps 30 gigahertz region.
Okay. Yeah.
So again, Rob comes from the radar industry and thinks about things in microwave terms. And I understand his first interest in GaN was when he needed a power supply for something he was building, and took a look at these fast switches and came to the conclusion there was nobody out there using them effectively. What they've been able to do is just think about the way that you would build an inverter to take care of all of the issues that start to come up when you want to run at really fast speeds. So they've just been focusing on how to do it better.
Yeah. Okay, cool. So just conscious of the time, bringing it to a close now, I always ask guests, what they're most excited about, in looking forwards into the future. And I'm guessing there's a lot that you're excited about looking forward. So, if you had to pick 2 or 3 things, 1 or 2 things that you were really excited that are coming down the line, either within the businesses you're working with or in the wider industry, what would they be?
I think, first of all, the new generations of gallium nitride transistors, but seeing the possibility now of working at higher voltages, I think with the QPT technology, we can address the amount of power that's being wasted across all of the motors in the world. And that's about half, a little under half of our use of electric power. A very large part of the rest of that is in distribution of that power. So with higher voltage GaN switching faster, or even silicon carbide. For me, it's fast switching devices. It's not just GaN. I don't have just a GaN hat any longer. I'm fascinated by switching things much faster and saving a lot of energy as you do it. So grid and distribution is an area that's it's just an enormous great field that we can go play in.
Yeah. Oh, fantastic. And obviously, it's talked about all the time of the fact that grid industry in particular has been so slow moving, and people are going to get it. Actually, it needs to change. So there's a lot coming there, and you can just start to feel that change coming through now. So brilliant. Well, I think that's a really good point to bring to a close today. I think we probably could have gone on for the rest of the day, Geoff, to be honest. It's always an absolute pleasure to talk to you, and thank you so much for agreeing to do this today.
Thank you for giving me the opportunity.